What's up, guys? Today is another video of robotics Q&A on the Robotic subreddit, and this is the Slate Robotics podcast. My name is Zach Allen. Podcast here is not exactly accurate for anybody who's listening. This isn't maybe the best show to listen to, but we'll be using the whiteboard. I'll be going through some questions through here, and I've got 7 questions picked out today. And I've only got about 45 minutes for this video, so I'm going to have to keep it brief today. But I hope you guys are having a good week. Let's just jump right into it. First question that I've got for today on the Robotic subreddit is mobile robot in rough terrain. Hey everybody, I have a mobile robot for my university. Subject of my project is mobile robot in rough terrain. I want to build it as a 4-wheeled robot with suspension. Let's say that it will be something like in video below. And there's a link. We'll get to that in just a second. And why I'm actually writing this post is because I'm looking for some ideas about what this robot can be able to do. Building robot itself is just too little. My project subject don't specify what exactly this robot has to do. So it can do basically everything connected with rough terrain. My ideas so far: 1, remote control via Bluetooth; 2, transporting heavy things; 3, probably some obstacle avoidance. But what else? Do you have any ideas? Well, let's click on the link and see a little bit of what he's talking about. Or she. Man, I am always so bad about assuming gender. Okay, so here is apparently the type of robot that they are building. That thing, if you end up building it to be that large, that is pretty cool. I am really curious what kind of actuators you would use with something like that. I presume just really large motors. I don't know what all that electronics and stuff on the top of that is. But yeah, that thing is huge. Looks like some sort of LiDAR sensor on the front. Oh, cool. It's got 4-wheel steering. That's really cool. Dude, that thing is fast. All right. So here's my crazy idea for this thing. First of all, what is wrong with you for not having already the idea to make a go-kart out of this thing? I mean, you should put a steering wheel on the top of it, or you can have some like joysticks or something where you can, those aren't joysticks, like levers where you could actually like control the robot or something like that. And you could drive this thing around. I mean, that thing is huge. If you end up making it that big and that fast, you could have some fun making that thing into a go-kart. And then once you have it into a go-kart, here's my second idea. You need to install Open Pilot, which is a, let's see. Let me Google this for you. If you go to GitHub, Open Pilot. It's from a company called Comma AI. And I don't know what it would take to integrate with Open Pilot with some random robot. But this is a self-driving autopilot software that's open source, and you could potentially get that robot to be... Looks like they're increasing the list of supported cars. That's really cool. But anyway, you could integrate with Open Pilot, and you could have your go-kart drive around autonomously on the road, which is probably illegal. So, you didn't hear this from me, but that would be a cool project. You could try to do some other sort of obstacle avoidance, mapping, stuff like that. But, who knows? I don't know where you would be driving this thing around. I mean, that's so big. I don't know if you're... I mean, like, do you live in the city or are you like out in the middle of nowhere? I mean, if you're in New York City, you're probably not going to be able to do too much with this. But yeah, man, go-kart and Open Pilot and have this thing driving around autonomously. You would be set. I told you we were going to fly through these fast. I need to slow down for some of these or else this video is going to be like 5 minutes long. But question number 2. Best simulator to learn ROS. Hi, I am a university student studying computer science and computer engineering. I've been looking to learn ROS on my free time. I have been looking at VREP and Gazebo to help me simulate robots since I do not have an actual robot yet. Which one would be better to teach me ROS? Thank you. Now, I've never used VREP. In fact, I've never even heard of VREP. I had to look up what VREP even was when I saw this. But I've used Gazebo pretty extensively in the past, and Gazebo's pretty good. Really is pretty good. This question highlights pretty well like my problem that I have with the state-of-the-art robotics today. So he's saying he's a university student, and he's wanting to learn ROS. And I guess just in his free time, right? Yeah, that's what it says. Looking to learn ROS in my free time. It's such a shame that universities don't have enough like classes on this stuff. And like here in Springfield, we have a couple colleges. The biggest one is Missouri State University. And they have one robotics class, and it's just working out of Gazebo. So they're just doing simulators as well. So they don't even have any robots that they work with directly. And it's such a shame that that's the case because, you can't beat working with an actual robot. I mean, the way I've used Gazebo and these kind of simulators in the past is that it's easier to like get the initial idea up and working in a simulation than it is to run it on a robot, because you can like close out of the simulator fast and like restart it and like reset the state, and you can do that like in a click of a button on the simulator. But when you're doing it on an actual robot, to reset the environment actually takes some time, takes some work. So simulators are really great for like you get your initial idea out there, and you're able to get kind of pen to paper, and then like that's half of it, and then the other half is like, okay, now let's run this on the actual robot and do all the fine tuning and get it actually to work on the real robot. Because there's always a little bit of a disconnect, particularly like the controllers that you're going to have running on a simulated robot. That's going to have different behavior than on your actual robot, and it's difficult to get those to match perfectly. So anyway, that's kind of a side note, but it is a shame that universities don't have actual robots to run on. Hopefully, we can once we start getting some of our robots out there, we can grow and sell some robots to some universities, because I presume the only reason they're not buying robots is because that's a big investment. Like if you only offer one class, I don't know what a professor would, like a computer science professor would make. I'm gonna guess not that much. I'm gonna guess you get summers off, you get vacation. I'm gonna guess like a university professor at just like a normal college is probably making like 60 to 75K a year at most, and then if they teach like, I'm just making guesses, if they teach like, we'll say 7.5 classes just to make the math simple there, then that's $10,000 a class. So the university effectively is spending like $10,000 plus the classroom, and the administrative stuff. Maybe they're spending $15,000 for a class, and they're not going to go out and buy a $60,000 robot just for this one class. They would have to have enough interest in it. They would need to build out like an entire robotics department in order to justify an expense like that. And most universities just aren't in that position. So, part of my hope is that we can build affordable but really capable platforms that we can sell to universities, and so that they can have access to actual robots, because simulation is only part of it, and it's a great way to get started, and it's a great way to learn stuff, but that the hard thing about robots is that you're dealing with actual physical hardware and things that are moving in the real world, and there's all sorts of unpredictable elements to that, and simulation just doesn't quite get all of that. But anyway, you're not making a mistake to use a simulator like Gazebo to learn ROS and learn more about robotics. I mean, you should do that, and if that's the best you got, like, you'll be able to learn a lot just from that. The other problem is that universities are just really difficult to work with. I mean, to find the right, well, they're expensive people to try to sell to. I'll say that. I mean, you can spend, so if I sell one university one robot, I have a profit margin that I make on top of any robots that I sell, and it's a good margin, but it's not crazy. So if it takes me 15 hours, and that, honestly, that's not too far off the mark. It might take me 15 hours of sales time to sell to these universities. Like, it's really not worth my time. Like, I'm better off just focusing on consumers and selling robots to them. So that's another part of the problem, is universities are really difficult to sell to. They're difficult to find the right people. Most administrators don't even have control over their own budget. I mean, some committee decided how much money they can spend, and that's it. That's all they can spend for the entire year. So they've got, you walk into their buildings, they've got millions of dollars worth of equipment, but you ask them to spend $15 on something, and they'll go, it's not in the budget. So it's pretty crazy. Anyway, that's just a bunch of tangents. Yeah, I'd use Gazebo, just because there's most people have worked in Gazebo. Gazebo has a larger user base than some of these other simulators. Again, I've been doing this stuff for a long time, and I've never even heard of VREP. And it helps if there's a little bit of talk here about computer performance. That's not too big of an issue. I've ran Gazebo on computers, on smaller computers, on computers that don't have a GPU, and it runs okay. If you have a GPU on your computer, then that's going to help tremendously with getting Gazebo to run properly. But anyway, and Gazebo's free, so can't beat that. Next question. Question number 3. Is it difficult to build robotic hands that do actual massaging like a real human? When I hear massage, I think of someone lying on the stomach and a man/woman grabs the back, shoulders, neck, etc., like in TV shows and movies, but current automated massaging devices are far from that. 1. Chairs. They just vibrates. They don't grab. 2. So-called massaging robots on YouTube. They have some rotating weird thing, not grabbing hands. Also, they are large and bulky. With our current technologies, we can't build 2 robot arms with hands that grab like a real human? ? Oh, I love these. Using a camera, the robot can identify human body. Smartphones can detect faces in a picture, so I think detecting human necks, shoulders is possible. Then the arms can move to gently grab the human's body. All it needs is 2 arms and a camera like a chess-playing robot. So I guess it does not have to be big and bulky like a chair. Of course, I have no skills to build such a robot myself, but I would like to buy but I would like to buy if such thing is commercially available. And I think a lot of other people would like it too. Do you think such robots are feasible with current technologies? I love all the spelling errors and weird sentences. So you're asking about. Well, the actual question is it difficult to build robotic hands that do massaging like a real human? The answer is yes, very much so. Let's see, where to begin? There's 2 parts to that. One is the whole safety problem, which is well, systems malfunction, right? So, you know, cars break down. Um, you know, there's programs and software have failures. So your number one problem is like you have a robot that supposedly is strong enough to actually like where you feel where the massage like actually does something. And what if, you know, some code runs awry and this robot starts like smushing you or hurting you in some way? You know, that's problem number one, is that there's I don't think there's much you can do in terms of preventing that capability or that problem. Number two, massaging is like it's more feeling than it is visual, right? Like when your eyes don't help much when you give someone a massage. Like it's more of like feeling, okay, that's a knot, you know, here's the tendons, you know, and you're feeling your ways in terms of where to push. So the robot would need some really serious like tactile feedback. And I don't know of great technology that exists currently that would be that fine-tuned. I mean, there's force sensors, and you can do force sensing resistors like in the thumbs or something like that, or if you had some sort of pressure, and you can judge force. But in terms of the robot being able to actually like feel the grooves of the back, if there's any technology that exists out there that can do something like that, it's going to be really, really expensive. I can tell you that. That's interesting. I mean, you could try to put torque sensors, and you could try to like map out like a person's like back or something like that, and you know, it could search for particular ridges that it needs to push on. Again, assuming that, you know, this robot is safe and it's not going to hurt anybody. I mean, so to answer your question, yes, it's a very difficult problem, and you know, the reason almost all massage devices are just like a motor with, you know, a spinning. I mean, I guess it's like probably got some mount with like, you know, these little balls on the end that just rotates back and forth and vibrates a little bit. It's because that's a really simple system. It's you know, it can be a fairly inexpensive system, and it does like, you know, 80% of what you would want a massage chair to do. You know, it would be nice to have more, but it starts to get cost prohibitive at that point. Like I would be like, there's some really expensive robots out there that don't have anything, any technology that would be necessary to have something like this. So yeah, I don't know. If I was starting to build something out like this, I would first try to figure out how you could run we'll just say like a finger or something on the end of a robot and actually map out every little bump and ridge in the robot. And, you know, maybe the problem is it's going to change. So like you would have to map it out in real time. You know, you can't just like run something over someone's back to like feel everything out and then go through to those points that it's identified. Because, you know, people move, you know, if I move my shoulder blades around, that's going to change kind of what the shape of my back looks like. So it would have to do it in real time. And it would have to be able to judge the firmness, and it would, you know, okay, that's bone. I don't want to press the bone, but this area is a little bit softer, which is muscle, but it's a little bit tenser, so I know it's a knot. So it's softer than like normal muscle tissue, but it's not as hard as bone. Yeah, it'd be really tricky. I would start with trying to figure out how to map out the back in real time using force sensors, torque sensors, and, you know, I don't know, some sort of like under actuated system, perhaps. Yeah, it would be a hard problem. It's probably there might. This is one of those where there might be a solution out there that is really simple and cost efficient. I wouldn't be surprised if there wasn't some way to do this that didn't cost a bunch. But you're gonna have to figure out something special that other people have missed when working on this problem. So this is one of those where I wouldn't be surprised if there's some sort of secret that we haven't discovered yet. Yeah, good luck on that project. That would be cool. Just don't, if you need someone to test it out on, you're gonna need to find somebody else, because I don't want to get near that thing. Okay, for our most downvoted question of the day is want to build a large, almost human-sized spider robot. Hello. I don't know the etiquette for this sub, but I was wondering if I could get some direction on how to build a large spider robot. I was wondering if I could make Hal's Moving Castle with legs moving. I've never heard of Hal's Moving Castle. Let's look up Hal's Moving Castle. Okay. Kind of like I suspected. Wow, that would be a big... So want to build a large, almost spider-sized robot. I mean, it's definitely possible. I mean, the reason questions like this get downvoted because it's like, what am I supposed to do all of your work for you? I'm not afraid to do all of your work. I will take a stab at this. So, let's think. A spider. I mean, let's just talk about like the design and the joints first. I mean, spiders have 6 legs, right? Yeah. So, the nice thing about this, if you design 1 leg, you just multiply that times 6, and you've got the robot. So, like, this could be a really simple robot because you only need to design 1 leg, and each leg only has like, let's think. So the leg has to, it needs to rotate back and forth like this. Like this is mounted to the body, so it needs some sort of joint here to pivot back and forth for walking. So this is looking down, and then really, I think you just need 2 joints, right? I don't think you need anything else. And this would rotate like that. So it would be able to, so if this is the leg, it can rotate back and forth like that, and it can also go like this. So in order to step, it would kick this leg out, move this forward, drop it down, and then move forward like that. And it would do it with all the legs at once. So yeah, this is really simple. Now, with anything above like a little desk-sized thing, so if you're building a spider robot that's really small, all you have to do is just go out and buy some standard servos, and you can attach them in each of, like you can buy some like little brackets. You could attach the servo motor in each one of these brackets. Anyway, it makes it really, really simple to design something out like that if you just use servo motors. The problem you're going to have with a system like this is that you're going to need a lot of torque. Now you've got 6 legs all working together, so that helps a little bit. But if it's going to be human-sized, let's see. So what's the measurement for, like, so if you have the body like this, you have a joint here. This joint doesn't need that much torque. It's going to be more than a servo motor, presumably, if there's all this weight on the body. But you're not going to need as much torque here. Where you are going to need torque is with this joint out here. I'll just go ahead and do that. Those are the feet. So this joint is going to need to have enough torque to lift up the entire body. So this one right here will need let's see. It's been a while since I've calculated torque. Let me look up the calculation there. It's radius. See, I've got that written somewhere. Hold on 1 second. Actually, I'm not going to pause this. I'll leave that up to you. You're going to have to calculate the torque yourself. So calculate the amount of torque that's necessary for this to lift. So however long the legs you want. So let's say if you want it human size, gosh, I don't know, 2 feet. I mean, that's still pretty small. Are you talking like the body's like eye level? I don't know. We'll go with 3 feet for now. So the leg is 3 foot here, 3 foot here, and then effectively you've got this giant mass right here. So in the body perhaps is going to be like 50 pounds. I can tell you if this is the length of these legs, you're going to need a ton of torque in order to lift that body up. And your standard hobby sized motors and servo motors are not going to be anywhere near powerful enough to be able to do that. Now the good news is, since there's 6 legs, presumably you're only going to need 1/6 the torque to move 50 pounds. So the actual payload for this particular assembly this joint is really going to be 50 divided by 6. I would round up to 10 pounds and expecting this thing to load 10 pounds because there's going to be some coefficient of friction in this system. And, all of these joints may not all be synchronized all at the same time. So it would help if actually do a little bit more than 1/6 of 50 pounds. And this number can change as well. I don't know if the body is going to end up being 50 pounds or not. But if it's going to be human size, I mean, it might be pretty close. Once you fit a battery in there, something that's big enough to do all of that. You could use like hydraulics, but then you've got to have a compressor on there. So probably for something like this, I would do electronics. You're also going to need, so basically you're going to have to build your own servo motor, I think. There's really not anything on the market that would give you enough torque. That's a servo motor. So you're probably going to have to go out and buy your own motor and then your own encoder, so that you can measure the actual angle of each joint. So yeah, this is looking like it's going to turn into quite a big project, mostly because there's not a lot of people that are building. Well, there's not a big market for like off-the-shelf components for really big robots. There's a big market for small robots, but not for big robots. So that explains the problem a little bit. I wish I could remember how to calculate torque here. Yeah. I've got those calculations hidden in some spreadsheet somewhere or buried in some spreadsheet, but you can look that up. I mean, it's on the internet. And you'll there's some element of acceleration. And anyway, I'll let you look that up. But that kind of defines the problem a little bit. But once you have that joint working properly, and you've got that designed, I mean, really, you're just going to reuse that 6 times. So, I would spend a lot of time just figuring out how to design these 2 joints properly, and then focus on how to design the robot around that, given what you need here. So, good luck with that. Next question. Need help with a creative solution for deducing joint position given motor position. I'm developing a robot arm as a learning project using an Arduino and stepper motors instead of servos. Each motor has an encoder on the back of it so I can read the position of the motor shaft. I would like to be able to store the joint position information in EEPROM at the end of every jog, so that if I shut the robot down and move some joints while it's powered off, the Arduino is able to discover the new joint positions when it starts up. For positions of the motors, I think it's pretty trivial, but the problem is almost all of these joints have gear trains on them. That means that the motor shaft position is only part of the equation for the actual joint position. I have all the gear ratio numbers, but I don't have any way to discover the position of the output shaft after power up. In other words, for a 50-to-1 gear ratio, there are 50 possible positions for every motor position. If you manually move the joint while the Arduino is powered off, I don't know how to discover the joint position once I've read the new motor position. Is anyone aware of a creative solution to accomplish this in software without putting the encoder on the output shaft? My holy grail is basically zero each joint during each calibration, then rarely have to worry about it again. So I think I know what you're describing here, because I personally have ran into this problem before. And there's no free lunch here, I'll say that. So just to make sure that I just understand the problem properly. Okay, so I'm presuming you're using a motor kind of like this. So you have a DC motor. I don't know this for a fact, but this is what I'm guessing. You have a DC motor. You have probably some Hall effect sensor encoder on the back. And then you have you mentioned 50-to-1, but it might be different. Gearbox on here. And then your output shaft is the output shaft of the gearbox. So as your motor rotates, you're able, and while everything's turned on, you're able to read the changes in the encoder, and you're able to deduce what the angle is, or really the change in angle. That's the only thing. You can only measure the change in angle using the encoder. And if you miss these encoder ticks, then like if you don't read these pulses that the Hall effect sensor is sending back, then you actually missed changes in output shaft position. So that's where some error can be introduced here. So you're saying you have this thing running and everything's fine and dandy, and you're able to read the changes in angle, after you calibrate, and that's great. And then you turn it off. You say you're storing all of this information presumably in an Arduino in EEPROM. That's also good. I think that's great. You can turn it off and you can turn it back on and everything works. But if you turn it off, you turn the output shaft and then you turn it back on, it doesn't know that the angle has changed. So you've gone from 50 degrees to now 60 degrees while it's turned off, and then you turn it back on, but it still thinks it's at 50 degrees when it's actually at 60 degrees. So you're saying, can I read changes? Now, let me see. I don't think you specify what kind of encoder you're using. No, I'm going to assume it's an incremental encoder. It's just a normal Hall effect sensor, and it reads the pulses as the shaft turns. So the answer to this is there's no way. It's impossible to know that the motor shaft is in a different position when you turn it on versus when you turn it off. So, some ways to get around this is kind of like with a 3D printer that has stepper motors. Those stepper motors don't actually have Hall effect sensors. Instead, it just has these end switches that it can use to calibrate the 3D printer. So the way 3D printers work, if you turn it off and then you turn it back on, it has to go through that calibration routine every time that it turns off, because those motors could move, If you turn it off, turn it back on, and you haven't touched anything, it presumably would be okay to use again, but it just assumes that I have no idea what's happened while it's been turned off. So everything just recalibrates from there. So really that's your only solution if you're using a setup like this and you don't want to put an encoder on the actual joint or the actual output shaft and read the output shaft directly, because this is where so much error can get introduced. So yeah, you could have some sort of calibration routine that it has to run anytime that it turns on. That would be my recommendation if you're really focused on keeping things simple on the mechanical side. Now I do want to talk about the benefits of actually reading the angle independently. So let's say, an example with our custom servos that we use for the TR2, we read the angle independent of the motor. So we could have a similar setup where we have an incremental encoder at the end of this this motor. But the problem is there's a little bit of play because the gearbox isn't perfect. So there's a little bit of play in the output shaft. And that's all play in the gearbox, right? So the incremental encoder wouldn't read those changes, because it's just the space between the gears up here. So this never actually knows anything changed. So I didn't even bother with an incremental encoder on our servos that we use. I actually use a separate encoder over here that in the way this is set up, it's got an internal gear. So we'll say so this is an internal gear on the inside of this cap, and as the motor turns, the encoder also turns, but this encoder is completely independent of the motor. So what happens is and also this is a absolute encoder as well. So if anything changes slightly whenever the thing's turned off, since this is an absolute encoder, it still reads the same position. So you don't actually need, you're not reading encoder ticks. You're just reading position that's given to you from this encoder here. So using an absolute encoder, but that actually doesn't account for everything here. Now, because we have a 3-to-1 gear reduction from the gear here to the output shaft, or to the internal gear of the cap. So there's a 3-to-1 gear reduction. So in theory, actually, if you took the cap and you turned it, we'll say, 180 degrees, then you turned it back on, the encoder would actually think that the position is different than it actually is. So we actually don't account for all of this problem. But the thing is, we're not using a 50-to-1 gearbox. We're using a 750-to-1 gearbox, which means that this motor is not back drivable. So it's impossible to actually turn the shaft or turn the output of the actuator if everything's off. So that's actually not a problem we have to worry about. And since this is absolute, we can store that position in EEPROM, and that's how I get around this whole problem. But reading the position independent of an encoder at the end of a motor is really important, because you can have some play in the motor shaft, either from the mounting hub that's on the shaft itself or from actual play in the gears, and that's okay. That ends up not being a problem because we read the position separately and independently of the motor, and this encoder actually will know that something's changed even whenever something like an encoder didn't. I was hoping whenever I first was designing this whole thing that, oh man, 750-to-1 gear reduction. I've got this incremental encoder on the back of it. I'll be able to read angles down to 1/1000th of a degree, right? I'll be able to have this thing super precise. And then I realized, well, there's play in the output of the shaft that this encoder doesn't know about. So I wasn't actually able to get that. But I do get down to about 1/10 of a degree using this absolute encoder. So it ends up being really, really good. So anyway, that's how I would do it. Now our custom servos are a little different than maybe your setup. And if you are using a 50-to-1 gear reduction, let's see. Let's see. So we'll keep everything 1-to-1 for now. So this is your actual. So we'll say all of these are 1-to-1. Okay, everything's looking pretty right now. Okay, so this is your absolute encoder. This is your motor. This is the actual gear for the output of the thing that you're wanting to move. Bear with me. I know this is all looking ugly, but this is the way I would set it up. And if you keep these angles these gear ratios 1-to-1, and you use an absolute encoder here, and you measure you measure the actual joint directly and independently of the motor, then you don't actually need to store anything in EEPROM because these absolute encoders will do all of that for you. So all you have to do is just request the angle from this encoder, or actually the position, and it'll tell you that directly. And again, you get the added benefit of you can have play in this system and you'll be able to actually measure it using the encoder because it's independent. So you obviously do what you want. You can either just do the calibration routine if you don't want to go back and actually redesign everything, or if you're looking for potentially a better system, I would suggest trying to measure everything independent and go from there. Yeah. So good luck on your project. Let's see. I'll erase that in just a second. Next question. See, we're gonna have to wrap this up pretty quick. Okay, contending with play in servos. Hi, I've been using RoboStar 3216 HTG servos in my robot, and I have been having trouble due to a rather large amount, 2 to 3 degrees of play in the position of the servo horn. Even when the servo is powered, since the servos are being used in the ankles of the bipedal walker, the play causes it to be incapable of even standing up straight, much less walking. I'd be very grateful if anyone could offer some suggestions in dealing with this issue. Basically, you're going to have two separate solutions to this problem. Number one is going to be just using another servo. Use a better servo. I didn't realize how stupid that sounded. Well, you could use like a motor. Just use a higher quality servo. Next question. No, I'm just kidding. If you're dead set on using these servos, you could do kind of what I was just talking about, which is measuring the angle independent of the servo itself. So the servos have a potentiometer in them. First of all, potentiometers are fairly good, but they're not great, because they're going to wear over time. The resistance is going to change over time as well as the more they get used. So those presumably aren't going to last forever. So that's something to know about. They don't actually use an encoder, or most, I don't think. I'm going to guess this one doesn't, because I looked it up and it's just kind of a normal hobby servo. But yeah, use another separate encoder to actually read the changes and try to account for that floating of the joint. There's probably something wrong with the gearbox, if that's the case, but I don't know. These are cheaper servos, so they're not designed to be precision devices. So honestly, if I were you, I would probably just look for a higher quality servo. Let's see, what is the company? It's Dynamixel. They make really great servos. And then also, some people have talked about like attaching, like here's one comment that says attaching a rubber band to the joint. I've seen that a little bit. And that's not a bad idea, but you're still not escaping the fact that there's this play that's unmeasured, and really that's the problem. You have changes in angle that you can't measure, and the best thing to do is just measure those changes in angle and measure the output of the joint directly, and use that as the well, basically, you're going to be setting a goal position. I want the angle of this joint to be this, and then any controllers that you're running that are in charge of making sure the joint is at that position, if there's any play in the actual joint, even if there is, once you move it, the controllers will step in and say, no, this is not the position we need to be in, and it'll kick it back. So either use better servos or use use an encoder separately. I mean, you might be able to get away with using one of these, using some sort of thing that keeps it, okay, well, let's say this is your motor shaft. So we're looking like down on it, like that. And then you've got so this is just describing kind of how you can get, how you can actually get play in these systems. So let's say we've got this, so this is actually your mounting hub. The play is actually in the gears, right? But this kind of describes the same sort of problem. And then you're going to have a set screw that you can sit in here to keep everything tight, right? To keep this mounting hub tight against this shaft. But the problem is, if everything's not perfectly aligned, and if there's not enough force on this screw to press down against that flat part, then you can see there's actually like a gap here in between the set screw and the shaft. So you could twist it a little bit without the actual shaft moving. So that's just an example of how you can get play in these systems. And there's precision equipment out there, and there's precision components, and there's ways to account for this. You can also use JB weld, but if the backlash is actually in the gearbox itself, there's not going to be much you can do about that. So what they're suggesting is to basically, we'll just say there's something over here that's in a fixed position, and you're going to take like a rubber band and tie it around that, so it's constantly, since there's play this way, it's constantly pressing it over here, and keeping, making sure that it always, if there is room for backlash, it's always, one direction. That's presumably an okay solution, and depending on what kind of robot you're building, and depending on if that's if you need continuous rotation, that's probably not going to work. If you have a limited range of movement, that could work. That very well could work. So, but if I were you, I'd either use a different servo or measure the angle independently of the servo using a separate encoder. Next question. I think last one. This is great. So I mentioned on the last one, I mean, literally this question is every week. And here it is again. How to learn more about robotics. So I came across this video of Japan's robotics. I'm fascinated and want to learn. Fascinated with it and want to play around with robotics like this. Currently, I'm a third-year mechatronics student at UOIT in Oshawa, Canada. And I know how to get started in learning more about mechatronics. and robotics. Should I start by learning about PLCs, or should I be gaining more knowledge about the topic to maybe eventually work for a company that deals with this cool technology? I'm planning on pitching this as a final year capstone project instead of a DIY 3D printed. Instead, make a DIY 3D printed 6-axis robot with grippers and controlled via joystick of some sort and start there. Pitch the idea to eventually turn into a robot that could potentially help the elderly at home and people who have disorders and can't take care of themselves, and the family members who are not living in the same household currently. Much appreciated advice or constructive criticism. Well, first of all, first of all, we should watch the video. I look at this guy. Look at this guy. This guy's the happiest he's been. That guy, not so much. So this is the video he linked to. Here's Toyota's. What do they call it? It's HRT or something like that. Anyway, this is one of Toyota's robots. This is a whole 25-minute long documentary, so I don't actually know which robot he's talking about, but presumably something like this. These things are really cool, and they are stupid expensive. My goal is to build one of those for $7,000 or $8,000. That would be game changing to the world of robotics. But anyway, that's what he's wanting to do. I'm gonna have to wrap it up here pretty quickly. But so your question is, how can I maybe eventually work for a company that deals with this cool tech? Or it sounds like he might be wanting to start a company. I don't know. It looks like you might be kind of open to both. Well, I'll talk about both. First of all, if you're going to go work at a big company like Toyota, they are not going to have just one guy that builds these robots. They're going to have a whole team of people, and each person is. Now, I'll say I've never worked at a company like this, but I can only assume they're going to have a big team of people, and this guy does this one specific thing, and he does it really, really, really well. And this other person does this other specific thing, and they do that really, really well, right? So I would think having a little bit more of a focused skill set would probably be effective in trying to get a job there. So find the difficult thing. I would say try to be fairly niche in terms of where you kind of hone your skill set. And find the kinds of things that they might have some difficulty doing. I mean, with something like that, I don't know. I mean, it could be the low-level software programming of these kinds of systems and building out the network topology and the communication protocols and doing a really good job with that on the software side. It could be you develop an expertise for building these kinds of systems using electric motors and, or maybe you custom design your own servo motors that are super high torque and super high power. Because I'm assuming they're going to be using custom servos in there to run this thing. So I don't know. First of all, if you're wanting to go actually work at Toyota and do something like that, first of all, learn Japanese, and then after you're done learning Japanese, do something niche, because these are well-funded organizations, and they're not looking for guys like me that are just kind of a jack of all trades, master of none. They're going to be looking for specific people. You can also look on their job boards. I don't know. I'll look that up later, but maybe Boston Dynamics has an actual careers page, and you can look up the kind of people they're hiring for, but I'm going to guarantee they're specific. On the second one, if you're actually starting a company to build a robot to work with the elderly at home and people who have disorders and can take care of themselves, I actually have kind of a rant on stuff like this. Nothing wrong with you for wanting to start a company like that. It sounds great, but the problem is you, as a third-year mechatronics student at a college in Canada, probably don't know enough about the market of helping elderly people to really serve that market well. Whenever you have a company, you need to first understand the market and then build the product from there. It's the wrong idea to build the product and then go, okay, great, who can I sell this to? Because you won't know enough about the pain points of the people you're selling to in order to serve them well. So that's the problem roboticists make all the time. They start with kind of this like, it sounds really good, and nobody's going to critique you for trying to help the elderly, except for me. And, you mentioned people have disorders, can't take care of themselves. That's great, and people should be trying to help them. But if you don't, my whole point is, if you don't know enough about what their life's like, and you don't know enough about really, you don't have any real insight into how to help these people outside of just your everyday person, then your likelihood of getting in there and actually doing something useful is so low, you might as well not even do it. Or you could try to partner with somebody who really does have expertise there, and first say, I want to help them. How can we help? And build a robot around a specific pain point, rather than okay, I built this robot. Now let's try to find a use case for it. And I mean, roboticists, I think, make this mistake all the time. And again, nothing wrong with you. In fact, it's awesome that you want to help people. I would first recognize the fact that you don't know anything about the market, and I'm assuming you don't. You probably don't. And either if you're still dead set on wanting to help people, that's awesome. Find somebody who can work with you and partner with them. Give them half your company and say, I have an expertise in robotics. I want to help the elderly, and you know a lot about, you've worked with the elderly a lot. You know what it's like to live with particular ailments, and let's figure out some system that we can build to help these people, because they'll have a lot more ideas about it than you will. So anyway, that about wraps everything up for today. I have got to get going, but thank you guys for watching. Subscribe, comment, whatever. I'll be back next week with another one of these videos. These are going great. I'm enjoying the Reddit stuff because I don't have to prepare much, and it's actually pretty entertaining. So thank you for watching. I'll see you guys next time.